Okay, so the first example we'll be working through is this one here. I want to get this truss structure that's shown, and I want to go ahead and solve for the forces in all the members. Stole this from the textbook, so I think it was, what was it here? It was 6.51. They were technically asking for just a few of the members, but we're going to go ahead and do them all because why not? If for nothing else, to show how tedious it can be. So first things first, take advantage of a few facts. So we do know that the structure is symmetrical. The load vertically is going to be evenly distributed between the two supports. Based upon the facts that so each of the P's here, it's 20 kip. So the total we got 100 kip. So at C and at K, we've just got a vertical reaction support force of 50 kip. C would have a horizontal reaction if there were any horizontal forces to resist, but it doesn't, so it's 0. So that one's simple enough. So here we've got the structure as a whole, and a free body diagram of the structure as a whole. Next thing we can do to simplify things is identify and remove any zero force members. So I'm going to zoom in on this a little bit. So we know that right here we've got one of those setups with two horizontal lines, two members that are that together form a horizontal line, and then a third member coming off of it. So based upon that, we know that this line here, JK, that's a zero force member. So we can just go ahead and eliminate that. And same idea here on this end at BC. We can eliminate that one because it is also a zero force member for the exact same reason. So I'll just redraw the diagram, omitting those members and labeling the dimensions as well. So there's 6 feet in between each of the sections here, and there's a steady rise here from the tip to the top, gaining an additional 2.5 feet per section. So in total, from here to here, that'll be 7.5 feet. So that's about all we need to kind of get things going. So we can just do an analysis at one of the points. So I'm going to start over this corner A here. So just drawing a little free body diagram of the joint itself. We'll have 3 forces. We've got the force in member AC right here. We've got the force in member AB, and we've got the load, the 20 kip load. Now, this is, as I mentioned before, the convention that we're going to be using is that anytime you don't know the directionality of the force you're working with, the default assumption is that it is in tension. So we'll orient those forces that the members are imparting upon the joint as if they were in tension, and then eventually we'll find out whether or not one of them is in compression or not. Glancing at it, it's obvious that at least one of them will be, since otherwise, we wouldn't have a balance of forces in the x direction. But in order to kind of translate the magnitude of those forces into x and y components, we just we need to calculate the unit vector, at least for the one that's for AB. AC is obviously, it's horizontal, so its unit vector is just in one eye in the x direction. But so the unit vector component for the x direction for AB, that's just going to be the 6 feet that it the 6 feet that it moves over in that distance, divided by the total diagonal distance there, which is going to be equal to just the square root of 2.5 feet plus, the square root of 2.5 feet squared plus 6 feet squared. Pythagoras' theorem gives us a distance there of 6.5, and so we can just keep it like that in order to eliminate some rounding errors, I guess. For our dy AB over dAB, so the j component of our unit vector, that's just 2.5 over 6.5 feet over feet, obviously. Units cancel out there. So we can go ahead and figure out what our y component force balance is. So we're going to have the positive component, the 2.5 over 6.5 AB, so the y component over AB, minus our 20 meter load equals 0, and then we can just solve for the force in AB as 52 kips based upon that. And then we can move over to the x direction. So again, we'll have the 6 over 6.5 portion, that's the x component portion of our FAB, times what we calculated the FAB as in the next step, plus the AC equals to 0. So basically, we to solve for AC, take this, subtract this to move it to the other side, and then that gives us a force in AC of negative 48 kips. So that's telling us that the AB member is in tension, and the AC AC1 is in compression. Which makes sense. So now we got that. So we can just move over to the next one. The next one we can solve. So I'm going to just move over to B. So at B, the diagram here. So at B, you've got the FAB, you've got the FBD, and you've got the FBC. But we already determined that FBC was going to be equal to 0. So our free body diagram turns into our FAB and our FBD being equal and opposite. Therefore, BD is equal to 52 kips as well. So they're both in tension. They're both positive values because they're acting in opposite directions. So moving over to C next. So at C, this joint right here, we've got the 48 kips. So that's the FAC. And that's 48 kips that's pushing towards the joint instead of pulling because it is in compression. And then we've got the unknowns here. So CD and CE are unknown. So we denote them as assuming their intention at this point, and then we'll figure out what they actually are once we do the math. Obviously, they can't be both intention because otherwise then this thing would not be able to be in equilibrium in the x direction. So again, just need to for the CD, we just need to figure out kind of the unit vectors for the unit vector components for the y and the x-axis. So for the x-axis, again, just the 6 feet from section to section, and then divide it by the distance of that member CD. It rises 5 feet in that section. It moves over 6 feet in that section. So its distance is just going to be equal to the 7.8102 feet. The y portion of its unit vector is 0.640. The x portion of its unit vector is 0.768, and so we can use those to solve for our equilibrium conditions at this joint. So starting off with the sum of the forces in the y direction, we have a positive 50 kips from our reaction, and we have the 0.64 times CD. So obviously CD in this case actually needs to be a negative value, so it needs to be in compression, and then the 50 divided by the 0.64 gives us negative 78.1 kip. And then next thing to do, just same deal but for the x direction. So we got the 48 kip, we got plus the C and plus the x portion of our CD. So again, keeping in mind you need to keep your unit your signs consistent. So the fact that this is in compression needs to be taken into account. So that's why you need to ensure that you do throw your negative values in there. So it's simple enough from there to solve CE as being 12 kip. So moving on next, we've got our D here. So we've got the 2 known forces and the 2 unknown forces. So we've got the 52 kips coming from BD. So again, that's in tension. So it's pulling away from D. I've got the 78.1 kip that's coming from CD. That's in compression. That's pushing towards D. And we've got the unknowns here. We've got DF and we got D. D is acting directly downwards, and DF here is, well, say if DE is in tension, it's acting directly downwards, and then we got DF as well. If DF is in tension, then it's acting along the same direction as BD and AB were, because it's the same angle there. So yeah, simple. Again, we know the unknowns. We've got the angles we're working at, so we can just solve for that. So the sum of the forces in the y direction. We got our 52, our minus 52 here, because it's, this thing's acting downwards, and then just times the unit vector component for that, and then we've got our 78.1 kip. That'll be a positive force in the y direction. So the 78 times its y component unit vector, and then we've got also added to it the df times its unit vector y component, which is the same as the multiplier for BD, because they're acting at the same angle, and then just minus d. Its unit vector y component there is just 1, so, or, well, negative 1. So then we can plug and chug, and we can solve for DE in terms of DF. So this ends up being minus 20. This ends up being 50. This ends up being 0.385 DF. So in total, just 50. It'll be 30 kip plus 0.385 DF. And we got that. So we can't solve that quite yet, but we can go a bit further. So we've got the forces in the x direction. So again, the component from the BD, that's going to be acting this way. So negative 52 kip times the unit vector component in the x direction for that angle, and our positive 78.1 kip times its unit vector component in the x direction. And again, I'd like to emphasize here that, again, you could be using unit vectors, you could be figuring out what those angles are and plugging cosine sines where relevant into there. Either way works. I like to keep things in unit vectors just because I think that, oh, sorry, I realized I was zooming in a bit off the page there. I like to use unit vectors because I think it just eliminates one source of error when you're rounding, as long as you're reasonable about kind of saving a bit of the rounding till the end, I think that either approach works, I guess. But I just don't like. I prefer to avoid having to keep track of angles too, if I can avoid it. But if need be, you can work with the angles. Anyhow, so got that, and then we also have the portion from DF. So again, it's got the same angle here as BD. So again, its unit vector component is going to be the same as well, and its direction. And it's based upon the assumed negative. Based upon the initial assumed it being in tension assumption that's the default, its direction is going to be positive. But when we plug everything in and then solve for df, it actually ends up being negative. So, yay, the math works out. So yeah. And once we solve for a df, then we can go back to this equation here that we had, and we can use that to solve for our dE. So our dE ends up being 25 kips. So again, that's a positive value. So the initial assumption that it is in tension is valid. So D is 25 kips in tension. DF is 13 kips in compression. Next one to go to solve for is at E here. So at E, we've got this situation going on. I got the negative 20 kip load. I got the 25 kip tension from DE. Got the 12 kip tension from CE. And we got these two unknowns here. We got EC and we got EF. So again, they're initially assumed to be in tension, and we'll see if that ends up being the case. So for EF, I just figured out what the Y and the X component of their unit vectors are. And we can plug in the forces in the Y. The sum of the forces in the Y direction is going to be 0. So it's going to be equal to 25 kips from DE minus 20 kips from the load plus the 0.781 times EF based upon its unit vector based upon its y direction portion of the unit vector. So again, that's simple enough to solve. I got the EF is going to be equal to the 20. Keep the EF on this side, subtract the 25, add the 20, and then divide by the 0.781. That gives us a value of negative 6.4 kip. So this EF here is actually in compression, and they're relatively small compared to some of the other loads that are in this structure. And then next thing, some forces in the x direction, simple enough. So again, got the minus 12 from CE. We've got nothing from D. We've got nothing from the load because those are both Y only. And we've got EC, and we've got the 6.4 kips negative because that's in compression, so it's actually pushing this way, times its x component of the unit vector plus our EC here. So solving for EC, it's just going to be equal to 12 plus 6.4 times the 0.625, which ends up being 16 kip. And then the next place we can go to, so we could either look at this joint here, or we could look at this joint here. We could either look at this joint here, or we could look at this joint here. I think I know which one I'm going to look at first because it looks simple enough. So if we go look at G, well, we've got got one of those situations where we've got a joint, but it's got 4 forces acting on that joint, but all of them they got opposite forces that are parallel to one another on either side of the joint. Two pairs of oppositely oriented forces. So again, that's one of those special cases that we had looked at. So we can just, based upon that, we can just look at it and say, all right, G is equal to 16 kip, because that's the magnitude of EC, and FG here is equal to 20 kip, because that is the magnitude of the load that is being applied at that point. And then there we go, problem solved. Everything else is going to be equal because this thing is mirrored. So basically, everything else is going to be mirrored. The structure is symmetrical, so the forces in any of the components are going to be equal to their mirrored counterpart. So, for example, IK and CE, we'll just locate those here. Like CE here and IK here, those are going to be equal. So we'd solve for CE, I think it was 12 kips. So because CE here is 12 kips, IK here is going to be 12 kips as well. And same can be said for each of these components. That's going to be equal to that. That's going to be equal to that. This is going to be equal to this. This is going to be equal to 0, and this is going to be equal to 0, but they're both equal to 0 because they're both identified as zero force members, and they're both identified as zero force members because they're the same loading situation. So that's about all you need to do in order to finish solving the rest of the situation. You know that when something is symmetrical, that about an axis, then you can just fill in. You can take advantage of that without any problem. So that's that.